it's important to understand what will become some linear combinations of normal random variables, so the random variables which are normally distributed. Let's consider the simplest case when we look at the linear function of normal random variables. For example, we're given a random variable which has normal distribution with mu and sigma, and a and b are some constants, and consider another random variable y, which is a times x plus b. And this theorem says that this new random variable is also normally distributed, and with this mean is a linear combination of the original mean and this variance. You see, we take the original variance and multiply it by a squared. How we can see this? Let me give you just formal explanation. So you remember that the function, the density function of the normal distributed random variable is the following. So here we have minus x minus mu squared over 2 sigma squared. So this was what we have in general for this random variable x. And how to show that y is also normally distributed? We need to show that its density function has the same form with this mean and this variance. If we look at the cumulative distribution function, let's denote it, let's say the cumulative distribution function for x like this, and let's take it at a point y. Okay, let's maybe start with cumulative distribution function for y variable for this new random variable. Then this is probability of y less than y, right? Which is probability, and y is ax plus b. Let's for simplicity assume that a is some positive number. Then this is probability of x smaller than or equal to y minus b over a, right? Which is in fact the cumulative distribution function of x of the original random variable at a point y minus b over a, right? And as you remember, the cumulative distribution, the derivative of cumulative distribution function is exactly the density function, right? So d fy, okay, let's maybe say that this is x, then fy, this is derivative of y. Okay, let's maybe write the letter y as a variable. Doesn't matter, in fact, just want to make it consistent. Okay, and the derivative of this is dy of this thing here, f of x y minus b over a. And what's this? This is derivative of, we use chain rule, right? Derivative of the function f of x at this point times the derivative of the function inside, which is just 1 over a. So we get this thing, and we definitely know what is the derivative of cumulative distribution function for the random variable x, since it's given that this is normally distributed. So this is fx at a point y minus b over a times 1 over a, right? And this function we know, this is written here. So this is 1 over, let me write it like this, 2 pi a sigma times e, and instead of x here we write this value, y minus b over a minus mu squared over 2 sigma squared. If we simplify this power here, you will see that this is 1 over 2 pi a sigma e minus y minus, if we find the common denominator, we get mu a plus b here, and this a squared, let me write it in here, over 2 sigma squared. And you see that this also has the same form as this one, as just normal random variable, but the mean value now, this thing, mu a plus b. And what is the variance? The variance is the product, sigma squared times a squared. Okay, so the important moment is that this new random variable is again normally distributed, but we have different mean and different variance. You can see on the graph, so this was the originally random variable x, which is given, was given mu and the variance, and you see what we get after taking linear combination, a linear function. This new random variable y, we has that the mean changed, right, also by the same function as is given, and the variance changed by the absolute value of a. Okay, so this is about linear function. Okay, what if we have two normal random variables? And for simplicity, we will consider only the case when they are independent random variables. Let's have a look at this theorem here. So assume that x1 is normal random variable with this mean and this variance. x2 is also normal random variable, but probably with different another mean and variance. Then if we consider a random variable which is sum of these two, it's again normal random variable. So again with normal distribution. But the mean is the sum of two means and the variance is the sum of two variances. Okay, if we ignore this word independent, what do we have here? We still have that the sum will be normal distributed, but for the variance we have some different expression with covariance. Okay, we will not going to write this formula. We just look at this simple case of independent random variables. Okay, so let's see if we have x1, the graph is here. For x2, the graph is here. If we sum them, you see how the mean and the variance are changed. So the mean just the sum, and the variance is the sum of squares of the variances. Okay, this is about sum of two independent random variables, and of course we can look at sum of n independent random variables, and it's important to understand that if we take, this is linear combination, and we can also add any number, so this is the most general result. So all our x1 and so on xn are normally distributed random variables with some different means and variances. And if we consider y as linear combination, this is also normally distributed random variable with mu, which is the same linear combination as y is, right? And the variance, this is sum of squares and multiplied by the coefficients squares. Okay, this is the most general result. And now let's look at the result when we will be mostly interested in averaging of normal random variables. So when we want to take an average, assume that we will consider that our xi are independent, and also they all, of course, normally distributed, and they all have the same mean and the same variance. Okay, and we will consider the average we denote it by x tilde or x bar, whatever. So this is average, so we take x1 plus so on plus xn over n. Remember, we already studied the mean and the variance of these two things, right? Of this average. So the mean was the same, right? So you can check that this is indeed true if we find mu. This is mu1 and so on mu n. So the sum of means over n. So this is n mu over n, which is just mu, right? If we're talking about the variance, so what we have to take, we take the variance of each, sum them, And we need to multiply by coefficient squared. The coefficient was 1 over n, so we multiply by n squared each time. So we get n sigma squared n squared, so which is sigma squared over n. So n times smaller than original one. So this is important, of course, to notice that average is again normally distributed with this particular mean and variance. Okay, and let's have a look at some illustration of this idea. So, for example, remember what we had. Let me add a page. Remember that, for example, the probability when we take one variance from mu, this interval was of 68%. So, of course, if xi are normally distributed, right, with mu and sigma. Now let's consider, for example, n is equal to 10, and let's consider the average. And let's ask the following question. What the probability of this average being in this interval? Okay, so what we have to do, the average, of course, we know that this is also normally distributed, right? And with the same mu and the variance sigma squared over n. So n is 10 in our case. So we can move from this one to standard distribution rate, which will be normally distributed, 0 and 1. And remember how we calculated this z. It was x minus mu over sigma, right? Or in our case, this was x minus mu over sigma over 10, over square root of 10, right? So because in our case, sigma is this expression. Okay, so now we are interested in this question, and this is probability of mu minus sigma, and this is, we replace with z. This is sigma over square root of 10 times z plus mu, right? And this is probability that we take mu away from everywhere, right? And we get minus. So here the sigma will be just cancelled. So we get square root of 10 for z and square root of 10. In fact, this is the square root of 10 approximately minus 3.16. And if you calculate it, this is in fact the cumulative distribution function at 316 minus cumulative distribution function at this number, which you can find using table, and you can find that this is 0.9992 minus 0.0008. So the result is more than 99%. So you see how high the result is for the average being in the same interval as each element is. So for separated elements we have only 68% being in this interval. But for the average we get more than 99%. Right? Let's move on to examples. Remember we talked about the radius of a piston head. So what we had there, some piston head and some cylinder. So the radius of piston head is x1, the radius of cylinder was x2, right? So this is some cylinder. And remember that the mean value for x1, the mean value was 30 millimeters, and the standard deviation 0.05. And cylinder x2 has the mean value, this one, and standard deviation, this one. And we consider the gap between x2 and x1. And the mean, of course, will be this expression, and the variance, so remember we already found it, was this one. So now if we know that the x1 and x2 are normally distributed, then the gap y is also normally distributed. Okay? For example, if we need to find, let's maybe ask some question here. What's the probability that the piston head will not fit within a cylinder? Probability that will not fit. So what is the probability of? So if it will not fit, then the radius of x1 must be larger, equal or larger than the radius of x2, right? So in fact, or we can say that y is less than or equal to 0. So this is in fact the cumulative distribution function. Oh, sorry, we have to move to the z. So if we change it for standard, normally distributed random variable, then y is equal to, so let me remind it what it was, z was y minus mu over sigma, right? So this will be z less than, so y is 0, right? So 0 minus mu over sigma. And in our case, this is mu is 0.25, so minus 0.25 over the variance, which this is variance, and we need its square root, so we need standard deviation, so we take square root of 0.0061. If we calculate it, this will be the cumulative distribution function for the standard minus 3.2. And if you go to the table and see that this is only 0.07% of this probability. Okay, so this how this can be done. Let's move on to one more example. Suppose that a wall is constructed from 24 concrete blocks. Remember, we had an example about concrete blocks. And the question, what is the distribution of the total weight of the wall? So we have some 24 concrete blocks, so probably maybe there are 6 by 4 or whatever. So some concrete blocks like this. Okay, and we know about each concrete block that, remember, we already looked at this example. Each concrete block is denoted by xi, and they are normally distributed with mean 11 and variance 0.09. So what is the weight of the wall y? It is distributed, right? As again is normal distribution. And when we talk about the sum, remember what we had. This must be the sum of 11. So okay, let me open this again. When we talked about the sum, doesn't matter, we can go here. So you can see that the mean is just the sum, and the variance is also just the sum, right? So this is 11 plus 11 plus 11, 24 times. And the variance, for the variance, we take 0.09 plus on 0.09, 24 times. Right? So in fact, what we get, this is normally distributed with 24 times 11, 264, and 24 times 0.09, which is 2.16. For example, let's say we want to estimate the total weight of this wall. Maybe we want the interval with the highest probability that we may get. And let's so remember what we studied, for example, the 99.7% chance that the wall has a weight within 3 standard deviations of the mean. So we take a mean and we subtract 3 standard deviations. Sorry, the standard deviations, not the variance. So we need to calculate the square root of the variance, which is approximately 1.47. So 3 times 1.47, and the mean adding 3 times 1.47. So if we calculate it, the interval will be 259.59 and 268.41. Okay, so it means that 99.7% that the wall has weight, total weight, weight in this interval, which can be really important information for builders. They can be confident that the wall weight somewhere between 259 and 269.